Today, my talk is about like two parts. In the first part of my talk, I will present some interesting results from a recent swarm in the Eger Rift. And in the second part, that I will introduce the large N network we are currently running in the Eger Rift. Before going to the Eger Rift, I want to introduce what are the seismic swarms and how do they look like in the rift systems. The seismic swarms are earthquakes that can be from the small size to the moderate size, and then they are mostly clustered and they are closing in time and space in a very clustered area. First of all, we have two types of basically swarms in the rift settings. That we have like dike-induced swarm in the rift center that they can be seen as at the shallow structures with the normal fault and the stark slip mechanism, and they can exceed over the kilometers. And this is an example of Ethiopian rift system. In the second kind, we have like fluid-induced swarms, what we observe in the Eger Rift mostly, that moho or mantle magma can be accumulated at the moho level, and then when they ascend upwards, they can create seismic swarms below the shoulders of the Eger Rift, and they can extend over broader zones at relatively deeper levels. And what we see in which region worldwide, that in Falkland and in Eifel region, in the also Eger Rift. So I want to introduce the Eger Rift and Hep Basin. They are located in the Central Europe at the border of Germany and the Czech Republic. And the region is well known with the earthquake swarms near the Novi Coastal area. And we have also very long-lasting radon and gas measurements. And the 3 to 4 helium measurements tell us that the source of this gas is mostly from the mantle level. And we have like recurring earthquake swarms in this region. And the region is thought like a natural laboratory because of the fluid fault interactions and magmatic hydrothermal coupling in the continental crust in an intraplate setting. So what about the regional seismicity? We have a like long catalog for this region, more than 40 years, that most of the seismicity was concentrated in the yellow part in Novi Coastal and Lubin along the Mariansky-Nazna fault zone. But last year in 2024, actually, that there was another point for the first time in the not in the instrumental, but the instrumental period, sorry. It was activated exactly at the border of Klingenthal and Krasnice. We worked in the detail, and you see also the station coverage is well done in this region with also the initiation of the ICDP borehole data that would also help us to work these swarms in detail. So now I will focus on this red zone that we worked in detail. As I mentioned, you see the seismic activity like in the northeast and southwest direction, and that it lasted for 3 months. Before this activity, that actually there was a smaller burst 3 months before than this at 11 kilometer. And then the earthquakes started here at the 10 kilometer, and they migrated upwards at the 8 kilometer. This also migration is a clear evidence of fluids in the system. And we found the normal fault, and you see the strike of the normal faults. They are really aligning very well with the strike of the seismicity, with the 57-degree faulting we found. And we located these events with the QSIC machine learning algorithm, both like using both German and Czech stations. And we also installed 2 more stations to the area to cover the spatial coverage. And also what we found, on the right-hand side, you see the comparison of borehole and surface data. We were very lucky that because we had very close stations at a 2 kilometer distance that we could resolve the swarm better. And actually more than 8,000 events we detected in 3 months, but what we have seen with the continuous data from the closest stations, there are many more events in the range of 100,000 and over. And this also could tell us that if we have like closer observations, we can locate more earthquakes near the source region. So the comparison of the focal mechanism with the recent swarm here, we see that you see here the recurrent episodic earthquake swarms with the red in the Novi-Coastal zone, in the main zone, let's say, that they show mostly strike slip and the thrust mechanisms. But for the first time, for this 2024 swarm, we have normal mechanism. This also has more implications about how the stress distributed overall in the region. And also we were lucky because the Falkland Eger Rift is well known with the historical observations that 130 years ago there was a publication by Hermann Kredner. He worked like a temporal evolution of this Klingenthal swarm and indicated that this swarm, this spot was also active at that time. Then he has a temporal evolution of the activity, and we also identified two different phases. Like in the first phase, these are our results. In the first phase, we have smaller events and then a lighter activity. But in the second phase, we see that the more larger events, and they last almost 2 months. And this is very similar to one that what Hermann Kredner observed. And I think this is a far comparison of two swarms in 130 years apart. And also he had ground shaking maps that we compared that the focal mechanism could fit very well to the ground shaking map, as he indicated. And what I said that we observed two different phases for this swarm. In the first phase, we see a bidirectional growth in both directions because of the overpressurized and buoyant body. And we call this an injection phase, that the water can go or gas upwards or downwards in both directions. But after the buoyancy is realized, that the fluid can also go to one direction. This is clear a backfront. Also, we know these observations from the induced seismicity, and it's called a hydrofracture model. And we model this first phase, but for this second one, we observed something different for the first time due to the intense observations. And after this phase stops, that the seismicity goes along all directions in a circular growth, which is a radial growth. And there is no back front visible in the time evaluation. These also tell us that less pressurized, less buoyant, but a denser material should follow the first phase. And this shows that how we interpret our results, that we have two fluids of batches. First of all, the lighter ones comes upwards, and then it introduced to the pre-existing fault system, and it creates a relatively smaller events with a narrow body. But then after that, there is a denser materials. We also derived the densities here for these two different batches. And this also goes to the pre-existing faults, and then it creates or triggers relatively larger events. And we interpret our density values with the geology and with the other studies in the region that we found this dense material could be carbolytic melts. And carbolytic melts, they are very important because when they interact with a neighboring geological unit, under phenetization and metasomatism processes, they can ascend upward, and when they ascend, they can also release some CO2 and then water, and then also they can carry some rare elements to the surface with an interaction of hydrothermal system. And finally, that what we can see on the surface are ore deposits, what we also observe from the geological maps for the Klingenthal region. And these were very interesting results, also gave us some encourage, and then we installed a larger network in the region. Now I will focus on this, that in August last year, we deployed 300 stations to the area to understand the swarm points better. Because as you have seen here, that the last 2 years of activity not only concentrated in Klingenthal, Also in Novi Castel, as always the case, but also in the south, in Francisco Belazne, in the Hep Basin, and also more to the south. But we have also some spots in the north, in German side. And also the B values differ a lot from one region to other. This is probably due to the insufficient coverage of the stations, or if they are real, we want to understand that what does this tell us about the stress regime and then the swarm dynamics, if there are also relations between two seismic swarm points. And these are the dark triangles that show the seismic network called ELISE, that we densified the stations near the swarm points, as you have seen here, as well as that we have a larger aperture with the broadband sensors to image the mantle transition and then crustal magma and fluid pathways beneath the Hep Basin. And we hope that our experiment will provide a better resolution to understand the swarm generating processes in an interpolate setting. These are some pictures from the field that we use the three different kind of sensors. First of all, we have mark sensors, short period, and the geophones, also the broadband sensor we have. And how we can deploy the stations, that we have like a large team, both from Germany and the Czech sides, that each team can go to the field with clear instructions, and this is how like a deployment layout look like in the end. And we record the data in the sampling frequency of 200 Hz. And for the field, we use the QField and QGIS applications to also work in parallel with the team and to update the station metadata in 24 hours. Here what I show is that one record section of this magnitude 2.5 earthquake recorded in September near Lublin and Czechia. You see that the red waveforms are from the permanent network already installed before than this ELISE experiment. The gray ones show from ELISE the waveforms, and we want to look at in details that some seal-like structure can generate that S reflections between P and S. This is something we observed now, but we want to go in detail. And secondly, that we also want to look at the anisotropy, because for the first time now we have many stations from different distances, with the same distances but from different directions, that also could give us like a higher resolution in terms of the anisotropy studies. So then we look at the noise levels, probabilistic power spectral density for each type of sensors. You see that we have a global high noise mode level and then the low level. And most of the stations are like showing very low noise. As you have seen also from the average values, that only in the Hep Basin we have relatively larger higher noise levels. It could be either due to the environmental issues or basin structures that can generate high noise levels.
Pinar, you're at 11 minutes now.
Sorry?
You're at 11 minutes now.
Yeah. And this is my last figure from the team, ELISE team, that we started to install the stations in the Czech Republic. And we aim to develop a coordinated interdisciplinary activity to study the role of carbonate-rich fluids and their interaction with the upper crust. And we want to understand the relation of this formation with the rare elements and the ore deposits also, which is one of the aim in the ELISE experiment. And I want to thank you all for listening to me, and I am happy to answer your questions.
Thanks a lot. Very nice talk, Pinar. Floor is open for questions. Please raise your hand or put them in the chat, and then you get the word. Maybe I start with one question. You have this data from the 19th century, which is really amazing. What other treasures of data do you have from that time?
From that time, we have some seismic catalogs just by him and ground shaking maps, like indicating that he probably spread some like polls to the region, to the people. And due to the the lack of that technology by that time, I think there were not so many other types of data.
Okay. Derek raised the hand.
Yeah.
Thanks for a nice talk. So you're linking the seismic swarm to some kind of CO2 rich fluids potentially. Is there any like evidence at the surface for an increase in the CO2 flux during the swarm?
Actually, the region is well known with the CO2 degazing, but we didn't have any measurement in Klingenthal directly. But as far as I discussed with our geochemist colleagues, that there is one station close to Klingenthal, but not so close, in 20 kilometers, that they observed some also increase in the CO2. We also try to understand with the gas and the seismicity in the next studies together.
Thanks.
Maybe I can add to this. And so it is maybe known that CO2 is monitored. So it's the aim of our observatory in this region to also have real-time monitoring. And in the past, sometimes there had been indications of possible correlation to earthquake swarms, and in other cases, not. So it's not a very straightforward and simple task to find these correlations. And there's one big unknown. Actually, nobody really can answer how fast would you expect that a transient of CO2 comes to the surface if, for instance, an earthquake swarm is in 10-kilometer depth. I think this is really an open question. Some say it's very fast, others say it's 10 years or 5 years. So the range really is enormous, which makes it also difficult to really verify that there are transients